All right. We're very pleased to have Arvind Suresh from UGA here to tell us about new points, more points. Yay. New points, rank growth, and the twisted Pruhata escort problem. Take it away, Arvind. You are
Sorry, I
mute.
was on mute. Thank you for the introduction, Padma. Thank you to the organizers. The last pajamas was awesome, and this pajamas is also awesome. Um, uh, so I'm here to talk about new points, rank growth, and the twisted Pruitt-Tarry escort problem. And here I've put the twisted in quotations because there was a classical Pruitt-Tarry escort problem, and this is sort of like a twisted take on that. Um, and so let me begin by just giving a sort of sample theorem, which is sort of reflective of the kind of things you'll see coming up. And so this says that if you have a chain of number fields, K contained in F contained in L, and here the Galois closure of L is M. And suppose you know that the degree of L over K is 16, and this degree is 2. Or suppose you know that the degree of L over K is 12, and this degree is 3. Yeah, under these hypotheses, there exist infinitely many elliptic curves over the ground field K, whose model Weyl rank grows both at this level and at L. Okay, yes, and a particular example of part A would be when you can take L over K to be any cyclic degree 16 extension, or I guess any abelian degree 16 extension. And the exciting case for me is the cyclic case. So let me begin by just giving you a quick outline. So I want to go over some definitions, in particular what I mean by a new point. I want to discuss the questions that I'm interested in or that motivate the stock. Then I want to go over the sort of the base for the stock is building on work of Master Shioda, Liu, and Lorenzini. Lorenzini is my advisor at UGA. And then I want to discuss the idea behind how I hope to, or how I guess I did improve some of these results. And then I want to introduce the twisted PT problem, which sort of arises from this idea behind the improvement. And then I want to just briefly state a couple of results that I have on this new problem. Cool. And so, given a variety x over k and an extension L over k, your x of L denotes the L rational points of x, or if you prefer, it's just if you think of x as living inside some projective space, it's just the points with coordinates in L. Okay, and we say that it's a new point if it's not f rational for any proper subfield, or equivalently, if the coordinates actually generate all of L. And what does it mean for them to generate L? Well, that means when you apply the action of Galois, then it has as many conjugates as it possibly can, which is degree of L over k many conjugates. And so another way of thinking about a new point is just a map from spec L whose image consists of degree of L many geometric points. Okay? And so a simple down to earth example is if you have the so-called hyperelliptic curve and you have a point with coordinates a, alpha, and beta, then it's a new point simply if the field generated by alpha and beta is precisely L. Okay. And so I want to consider a slightly more general notion, which it turns out to be super useful in what's going to come up. So recall that a finite étale K algebra is just a product of number fields containing K. And here, sorry, in the stock, everything is number field. And the degree of such an algebra is just the sum of the degrees of the extensions, or if you prefer, it's the dimension of A as a K vector space. Okay. And an A-valued point of X to give such a point is just to give a tuple of points, one in each Li. Yeah, so you have a P1 defined over L1, and you have Pn defined over Ln, and so on. And so, analogous to the field case, we say that this is a new point in X of A if the image consists of degree of A many geometric points. Okay, and so each color here represents the geometric points coming from one of the fields. And so you can think of each of these as like one Galois orbit, which maybe corresponds to one closed point on your scheme. Okay. And so here, the notation x of a sub nu denotes a set of points in x of a that are actually new points. Okay. And so just a couple of quick examples. Here's the totally split case when your algebra is just n copies of k. And in this case, to give a new point over k to the n is literally just to give n distinct k rational points. So in the particular case, when your x is the affine line, uh, so to give a new point over A is just to give, an element of the algebra. That is equivalent to just giving an element of each of the component fields. Okay. And in this case, there's a neat way to detect newness. It's just you look at the characteristic polynomial of alpha, which I remind you, multiplication by alpha defines a linear map, and it's just the characteristic polynomial of this map. And in this case, this is a new point if and only if the discriminant of this characteristic polynomial is non-zero, or equivalently, your alpha generates A as a K algebra. Okay. And I just want to point out that there's this nice functoriality in this definition, which is if you take a point in here, and by base change, you get a point in here. Here, x sub L denotes the base change to L, and A sub L is just A tensor L. Okay. And so if it's new here, it's also new there. And that's precisely because by defining it in terms of geometric points, it's a notion that's stable under base change. Okay, and in particular, if you choose your L to be a field M that splits A, in other words, once you tensor with this field M, it actually becomes just a bunch of copies of M, then giving a new point over A, sorry, if you can take a new point over A and then base change to M to get just degree of A many distinct M rational points. And so the driving question behind, or the first driving question behind today's talk is simply, what can we say about this set NP of G, K, A? And what is this set? It's just a set of K bar isomorphism classes of genus G curves over K, which have a new point over A. Okay, and just right off the bat, we can at least say something conditional on the weak Lang conjecture. So Pacelli has proved, and this is a strengthening of a theorem of Caporaso, Harris, and Mazur. They prove that if your genus is at least 2, then the weak Lang conjecture implies that that for large enough D, there are only finitely many genus G curves over L having D distinct L rational points. Okay, and this large enough depends on the genus and the degree of the number field L over Q. And this immediately implies a similar statement for new points over étale algebras, which is if your degree of A is large enough, then you know that this set is going to be finite. Okay, and so moving on, an abelian variety. Recall that if you have an abelian variety over a number field, then the Mordell-Weil theorem guarantees that the group of K rational points is a finitely generated abelian group. So there's a free part and there's a finite torsion part. And the rank of this abelian variety is simply the rank of the free part. Okay, and we say that this rank grows at L if the rank of this group J of L is strictly greater than the rank of J of F for any proper subfield F contained in L. Okay, and so the second driving question of today's talk is, if you have an abelian variety of dimension, if you fix a dimension G and you fix an extension L over K, can you find an abelian variety of that dimension whose rank grows over that particular given extension? And a more refined version of this question is, if you have a Galois extension M over K and you have a particular representation of the Galois group, you can ask if you can find an abelian variety over K such that this representation appears inside J of M tensor Q, which is a Galois module, I guess. Yeah. And so this is the basic outline for the ideas underlying today's talk, which is, so it all begins, like the story all begins with work of Mestre, which was later generalized by Shioda. And so they came up with this, I guess Mestre came up with the construction of hyperelliptic curves. So genus G hyperelliptic curves having many rational points, or in other words, in today's notation, it's a new point over K to the D, where D is large with respect to the genus G. So D is something like 8G plus a constant. And then also, so Shioda sort of took Mestre's construction and also showed that you can prove that the rank of the Jacobian is also large. And here I remind you that the Jacobian of a genus G curve is just an abelian variety of dimension equal to the genus G. And the Mordell-Weil group, the group of K rational points, is just equal to the group of degree 0 divisor classes on the curve. So it's sort of, it's this abelian variety whose group of rational points sort of encodes something about the geometry of the curve. Okay. And so this is the idea. How do we sort of expand on this? So the one thing you can do is what my so one way to sort of I'm blanking. One way to sort of extend the work of Mestre and Shioda is to go the route of Liu and Lorenzini. What they did was they sort of twisted this construction, and instead of producing many rational points, they produced curves with new points over like Adal K algebras. And here, saying that D is large, the corresponding statement here is that the degree of this algebra is large compared to the genus of your curve. Okay, and so my contribution to this aspect here is to also add in this part about producing explicit Galois representations of large dimension within the Jacobians of these curves. Another direction you can go is vertically upwards, which is, can you sort of improve on this construction to produce more rational points and greater rank than what Mestre and Shioda were able to produce. And so here, so this is actually the previous talk I gave at Pajamas like a couple of months ago, was I sort of related their construction to this classical Pruitt-Arey-Escott problem. I showed that you can harness the power of this problem to produce an improvement. And that actually gave new records for infinite families of curves with rational points and large rank. And so now today I want to talk about how you can punch this and this together by sort of, you take a compositum of these two, and this involves a twisted Pruitt-Arey-Escott problem, which, well, we'll see what it is. And what it results in is you get new points over Adal algebras that are larger than what Liu and Lorenzini are able to do. And also you get larger and better Galois reps, so to speak. Cool. So I want to first, I want to first sort of discuss this. And in order to do that, I just need to quickly introduce some terminology. So this is the basic setup. You have this chain of extensions, where as always, M over K is Galois. Okay. Your G is this Galois group. Your H is this Galois group. Sorry for being so informal. And so associated to this G and H, you define this representation of L, which actually doesn't really depend on M, and I'm being imprecise here, forgive me for that. And it's basically you take the trivial representation of H, and then you just induce it up to G, and that splits as a trivial representation of G and this degree of L over K minus 1 dimensional representation. And this I'm defining to be rho of L. And the fact that I've just put a subscript L sort of suggests that it's just some representation that can just be defined using data of L only. Yeah. And so Rohrlich showed that if you have an extension of bounded degree, bounded by 9, then you can find an elliptic curve over K such that rho of L appears in E of M, and this should be E of M tensor Q, my bad. Okay, and so here is the generalization. So here you take any positive integer G, you choose your Étale algebra to be a product of these LIs, okay? And you assume that the degree of this algebra is 4G plus 6. And then the statement is that there exists infinitely many genus G curves X over K, and these are hyperelliptic curves, such that, first of all, they have a point in X of A which is new. And so this is what Liu and Lorenzini proved, okay? And then the second part is my contribution, which is that you look at the corresponding geometric points, which are actually just M rational points, where M is just sort of the compositum of the Galois closures of each of these LIs, okay? Then you can sort of, there's a morphism from X to the Jacobian such that when you look at the images of these component points, these M rational points, they satisfy exactly one single relation, which is when you add them all up, you get 0, okay? And then, and so that implies that they generate a subgroup in the Jacobian in J of M of rank 4G plus, that is a typo. That should be 4G plus 5, my bad. And so the stronger statement is in terms of what the representation is that they generate, which actually can be deduced simply from this statement. It's just for each of the fields of the row Li that I just defined previously, and then you also have an extra q to the n minus 1, and here this q to the n minus 1 means that this is sort of like Galois acts trivially on this, and so this actually means that the rank of jx of k, over, like the rank of the ground field itself, is at least n minus 1. I'll just maybe give it a brief minute, maybe, so y'all can just imbibe this, like what this is saying. But then again, I'm running out of time, so I'm just gonna blaze through. Okay. Sorry. Okay. Just so for an example, just with elliptic curves, what you can do is you can take any field extension of degree at most 10, not 9 like what Routledge had. And then you can just pad up to 10 minus the degree with sort of copies of k, and then you get sort of this much rank over k, and then you get a copy of that representation over L. And in particular, if you take L over K to be a degree 10 extension with Galois group S10, and this gives you plentiful supply of elliptic curves whose rank grows over this degree 10 factorial extension, which is, I'm pleased to say, very large. Okay. Uh, and so these are just some other examples. You can take like 3 copies of a cyclic field along with 1 copy of K, and then you get like you get sort of elliptic curves whose rank grows by at least 6 when you go from K to L. Or you can take 2 copies of a cyclic degree 5 field and you get elliptic curves whose rank grows by 8 when you go from K to L. Cool. And so the idea behind this theorem is simply it's very concrete and down to earth. You sort of pick a basis for your algebra, right? So that any element can just be written as a linear combination. Okay, and it turns out that if you look at the characteristic polynomial of alpha, so this is an even degree polynomial. You can uniquely express it as a square minus a polynomial of small degree, which is, and this here the degree is d minus 1. And it immediately follows that if you consider this hyperelliptic curve given by y squared equals L sub alpha of x, this comes equipped with a point, p sub alpha, where the x coordinate is just the alpha that you started off with, and the y coordinate is 8 sub alpha of alpha. Okay, and so this sort of leads to this picture where you have a family of curves parameterized by the xi space. And so to choose a k point of this is literally just to choose an element of a, and then the fiber over such an element is just you're sort of parameterizing these diagrams where given such an alpha you get this curve and you get a point which sort of fits into this commutative diagram. Okay. And here this xi space, you may recognize this is just a restriction of scalars from a down to k of your affine line over a. And so the idea behind improvement, which I certainly do not have time to go over, is basically in a nutshell is you sort of want to choose your alpha so that when you look at its characteristic polynomial, it decomposes as a sort of like an inner polynomial of degree greater than 1 and an outer polynomial of even degree. And then the upshot is if the inner polynomial is of degree e, then your degree then your degree of your curve x sub alpha, like normally you would expect it to be d minus 1, but in this case it turns out to be d minus e. So it's dropped by like e minus 1 at least. And also it turns out that you actually get this lovely commutative diagram where, so this is what you normally get for any alpha, but if you choose this special alpha, which has this sort of composite characteristic polynomial, then you can extend this out into such a diagram like this. Okay. And so basically the point is then to sort of try to parameterize diagrams like this. So we want to find alpha which fit into such a diagram, and that actually leads to Prouhet-Arrhenius problem, which I will now state. So this, simply speaking, asks if you have K contained in B contained in A, and where this is free of rank E, and it simply asks, can you find a composite polynomial which generates A, and such that the outer polynomial generates B? Or equivalently, you can ask, is there a finite degree E morphism such that is there a finite degree E morphism and a B rational point of the target such that the fiber is isomorphic to spec of A? And I really love this problem because it reminds me of what happens in the case of arithmetic curves of like spec of OL to spec of OK, and then it's sort of like Chebyshev density or Frobenius density, whatever. It tells you a lot of pretty much it completely answers this question for you about what kind of splittings can happen. And so this is just the picture to keep in mind, which is these are your LIs, and then these are your points corresponding to the FIs, and then it's asking, can you sort of lift these like this? And so let me just quickly say, I'm out of time, that there is a variety that parameterizes these diagrams, and and it also parameterizes them in a nice functorial way, in the sense that if you base change, then parameterizes the diagrams over L. And the reason it's called the twisted PTE problem is because the classical PTE problem is just when all of these are rational points and there's no Galois action. And then you're just asking, can you lift a bunch of rational points via degree E morphism? Or can you find a bunch of rational points that split completely, or lift to totally split? You get the idea. Sorry. Okay. And then, so this is just a review of the low degree cases. And in order to actually apply this effectively to get curves of high rank and so on and so forth, we actually need these varieties to satisfy this thing called the Hilbert property. And I'll just say briefly that if the degree is 2, then it's an affine space, so we're good. The degree is 3, then it's an affine line crossed with an algebraic torus. And in this case, it follows from a result of polyethylene in Sansu that it does satisfy the Hilbert property, so we're good. The cases of degree 4 or 6, you can find proper positive codimension subvarieties that are principal homogeneous spaces for algebraic tori. And so there is actually a cohomological obstruction to having a rational point. But if that obstruction is resolved, then you're good. It does satisfy the Hilbert property, and so we can apply this. And so I just want to skip ahead really quickly. Well, I guess I'll just leave this theorem up here, and I just want to point out, I just want to say if there's anything that you take away from this talk, it's this sort of, to me, it's kind of mind-blowing fact, which I still, to be honest, don't really believe. I'm sort of worried that it's not true, but I'm pretty sure it's true, which is that if you take the polynomial x cubed minus 3x, okay, and you consider the map x goes to x cubed minus 3x, then for any 8 algebra B and any degree 3 extension A, you can find infinitely many B points of the target such that the fiber is isomorphic to spec A. And this is something like unique and only satisfied by this polynomial, and also, well, I guess cubic polynomials that can be sort of rearranged by affine transformations to be put into this form. Yeah, I never actually got to say what results we get by using the twisted PT problem, but I'm okay with that. I'll just end it with this. So thank you very much.
Thank you, Arvind, for the lovely 2-part talk. Any quick questions for Arvind? Well, I had one. What's special about this x cubed minus 3x?
Oh, because this works for any B and any A. That's of degree 3. So like you give me a number field of degree 1 million and an extension of degree 3 million. Then you can find infinitely many points with residue field equal to that first field, and such that the pre-image has residue field equal to that degree 3 extension.
But how did you find this? Like, was there a reason you knew this one would work?
Yeah. So well, if you look at this, how did I find this? So this is actually it was kind of, well, I can quickly describe the idea. It's like you start off with a polynomial in your you start off with an element that's of trace 0 in your cubic extension, and here the trace relative to the intermediate algebra, that's a trace 0. When you invert it, your 0 coefficient in the x squared becomes your 0 coefficient of x, and then now you just have a non-zero trace coefficient, and so now you can sort of just scale your element so that you can fix your trace coefficient to live in K in the ground field. And then again, you just do some kind of affine transformation, and it turns out that the polynomial you end up with,
you can churn it out by hand. You're saying using
you can explicitly cook up, this thing, yeah.
Okay. In interest of time, I maybe will say please ask Arvind questions on Discord. There's a whole channel to keep the discussions going.
Sorry for going over.
No problem. This is a very nice talk with very pretty pictures. I always enjoy listening to you. So thank you very much for coming back to give a second talk.
Thank you for having me.
Let me stop recording.